Every day we look up at the sky. Sometimes it is a perfect dome of blue, other times it blazes in fiery reds and oranges at sunset. For most of human history, this simple sight was a mystery. Why was the sky blue? Why did it change color when the sun set? Philosophers, poets, and scientists all searched for answers. Today we know the truth. The color of the sky is the result of physics, the atmosphere, and the biology of human vision. In this video, we will explore why the sky is blue, why sunsets are red, and what these colors reveal about Earth and other worlds. For thousands of years, people created stories to explain the heavens. The Greeks thought the sky's blue came from reflections of the ocean. Ancient Egyptians described the sky as the goddess Nut, painted blue with stars across her body. In India, early texts described the heavens as radiant with divine light. In medieval Europe, philosophers argued that the blue was the natural color of the celestial spheres. Even Isaac Newton, while studying light, could not fully explain why the sky was blue. It took the work of 19th-century scientists like John Tyndall and Lord Rayleigh to uncover the real cause, the scattering of light in our atmosphere. To understand this, we must first understand sunlight. To the naked eye, sunlight looks white. But in reality, it is a mixture of many colors. A prism splits sunlight into a rainbow: red, orange, yellow, green, blue, and violet. Each color corresponds to a wavelength of light. Red light has the longest wavelength, around 700 nanometers, while violet has the shortest, around 400 nanometers. This difference is crucial because shorter wavelengths scatter more strongly when they hit molecules, while longer wavelengths pass through more easily. Now picture Earth's atmosphere. It is not empty. It is a mixture of nitrogen, oxygen, and trace gases, with countless molecules and tiny particles. As sunlight passes through, the shorter wavelengths, blue and violet, are scattered in all directions. This process is known as Rayleigh scattering. Because this scattered blue light reaches our eyes from every part of the sky, the whole dome appears blue. It is as if the atmosphere becomes a giant lens, painting the heavens with scattered light. But if violet light scatters even more strongly, why don't we see a violet sky? The answer lies in our eyes and in the atmosphere itself. Human vision is less sensitive to violet than to blue. Our cone cells detect red, green, and blue, but violet triggers them weakly. In addition, the ozone layer absorbs much of the violet light before it reaches us. The result is that blue dominates our perception. So when we look up, the sky glows with blue instead of purple. At sunrise and sunset, something magical happens. The sun sits low on the horizon, and its light must travel through a much thicker slice of the atmosphere. Along this longer path, the shorter wavelengths, blue and green, are scattered away. What survives are the longer wavelengths of red and orange. That is why the sun itself looks redder near the horizon and why sunsets are filled with fiery shades. This effect is amplified by dust, smoke, or volcanic ash. After the eruption of Krakatoa in 1883, sunsets around the world glowed a deep crimson for months. Artists like Edvard Munch were inspired to paint the dramatic skies, leading to works such as The Scream. This scattering process is not limited to skies. It explains other phenomena we see every day. Distant mountains appear bluish because the light traveling from them scatters in the air. The moon turns coppery red during a lunar eclipse because Earth's atmosphere bends and scatters sunlight into the shadow. Even why the ocean looks blue is partly due to scattering, combined with the absorption of red light by water. On Mars, the dusty atmosphere gives the sky a butterscotch hue, and paradoxically, sunsets there appear bluish. Physics paints each world with its own palette. Alien skies across the solar system are even more diverse. On Venus, thick clouds of sulfuric acid produce a yellow-white glow. On Titan, Saturn's largest moon, a dense haze of organic particles blocks most sunlight, creating an eerie orange sky. On Uranus and Neptune, methane gas absorbs red light, leaving a deep blue atmosphere. By studying these skies, scientists learn about atmospheric chemistry, weather systems, and even the potential for life. Earth's blue sky is a gift of its unique balance of gases and sunlight. The science of scattering is not just something to read about, you can recreate it at home. Fill a glass of water and add a drop of milk. Shine a flashlight through it. From the side, the water glows bluish because the short wavelengths scatter. Look through the glass from the end, and the light appears reddish, just like a sunset. This simple experiment mirrors the very physics that colors our skies. Teachers often use this demonstration to make atmospheric science visible to students. But light alone does not explain the story. We must also consider biology. Human eyes contain 3 types of cones, each sensitive to different ranges of color: red, green, and blue. Our brains combine their signals into the full spectrum of colors we see. We are particularly sensitive to blue, which makes the sky appear vivid. But animals see skies differently. Bees can detect ultraviolet light patterns invisible to us, which help them navigate by the sky. Birds have 4 types of cones, giving them a richer perception of color. For them, the sky may appear in shades we cannot even imagine. Dogs, on the other hand, have fewer cones and likely see the sky as muted. The colors of the sky are more than beauty, they are tools for science. Satellites measure how light scatters to monitor air pollution, greenhouse gases, and the impacts of climate change. Astronomers apply the same principles to study distant exoplanets. By analyzing how starlight scatters through alien atmospheres, scientists can determine whether those worlds might be habitable. Climate models on Earth also depend on understanding scattering. Every shade of blue or red we observe carries information about our planet's health. The sky's colors also shaped human culture. Blue skies became symbols of freedom, peace, and optimism. Red sunsets inspired poetry, art, and religion. In Japanese haiku, the evening sky symbolizes transition and impermanence. In Norse mythology, red skies were signs of gods at war. Even today, the emotional impact of a golden sunset remains profound. We may know the physics, but the beauty still moves us. Looking to the future, the study of skies may help answer humanity's biggest questions. New telescopes will analyze how light scatters in distant atmospheres, searching for biosignatures. A world with a blue sky, rich in oxygen, might indicate life. By reading the skies of other planets, we could discover whether we are alone in the universe. The simple question of why the sky is blue could one day lead us to the discovery of another Earth. So next time you stand under a clear blue sky or watch a glowing red sunset, remember, you are witnessing physics, biology, history, and culture all at once. Light, air, and human perception combine to paint the canvas above us. The sky may seem simple, but it carries the story of our planet and perhaps the key to finding others like it. Subscribe to Why and How, and let's continue exploring the hidden science in everyday life. Instructions. Add smooth transitions between ideas. Highlight key concepts: Rayleigh scattering, wavelengths, human vision, other planets. Use stock footage of blue skies, sunsets, volcanic eruptions, mountains, lunar eclipses, Mars, Venus, Titan, and simple at-home experiments. Narration pacing. 11 to 13 minutes duration, 2700, 3000 words. Output a ready-to-upload video for YouTube.